of MIE404 2017. I'm Professor Amy Milton, and I'm your professor for control systems for this year. Controls is one of my favorite classes to teach, and it's been hugely influential in my career. I hope I'm going to be able to excite you with some cool applications and really interesting theory. I don't know if you ever heard really interesting in theory in a complete, sentence together before, but really it is super cool stuff. So I hope you're going to enjoy it. The introduction lecture for this class is usually one of my favorite classes to give all year. Unfortunately, this year, or fortunately maybe, I'm unable to give that lecture. I'm actually here in Ho Chi Minh City, Vietnam. My research group has put in an application for the Aquaculture Innovation Challenge, and we're finalists in that challenge. So I'm here in Vietnam to pitch our idea, see if we can get some more money to be able to take our research to the next level. I'll tell you a little bit more about that later on in the lecture, as well as I'm going to talk to you a little about what we're going to do in this class and give you some interesting examples of control systems from Vietnam. Well, to get started, I'm going to just give you an overview of what the class is going to look like and the structure of the class for this year.
So a bit more background about me. I'm an assistant professor, and I started here at the university in 2014. My research group is called the Water and Energy Research Lab. I'll tell you a little bit about some of the things that we do in a few minutes. And I'm also the Associate Director for the Center for Global Engineering. Outside of my research, I do many different things around the university, including being the faculty advisor for the Solar Car team. So if I look familiar to some of you, it may be from them. So before I started here at the university as a professor, I actually completed my master's and PhD at MIT. And then going way back, I actually completed my undergraduate here at University of Toronto in engineering science. So I remember what it's like to be a student. It was a little while ago, but I do remember. Outside of that education, I also spent a few years working in industry between my master's and PhD as a controls engineer at Pratt & Whitney Aerospace and Honeywell Aerospace. So to give you a bit of background on some of the research I've done really a broad range of things, from looking at developing sensors and instrumentation for marine observations, to developing robotics for space and mobility aids for the elderly. In my research group currently, I do a lot of work looking at water and energy systems. So it's a little bit of a shift, but the core things of what we do in my research group are still the same as what I used to do before. We're looking at being able to use innovative control and design methods to help tailor different water and energy systems. A lot of things we work on in my research group are technologies which are geared towards low and middle income countries, such as developing systems to be able to enable better water quality for fish farmers in the developing world, to developing technologies to enable efficient water treatment for people living in remote communities. So if you have any questions at all as we're going through the course, I want you to feel free to ask. You can obviously ask the question during lecture, just pop your hand up. If you have questions and you don't want to discuss with the rest of the class, you can always come find me immediately after lecture. And if those times aren't great either, I also have office hours, which are scheduled on Tuesdays at 5 to 6 p.m. in my office, MC311. If that time doesn't end up working well for the majority of the class, we can see if we can find another time slot which might work a little bit better. So at the university, we're trying to teach you numerous things. We're trying to teach you how to have good technical skills so you're going to be able to analyze tough engineering problems. We're also trying to teach you professional skills. And that's really to help you to be successful when you go out into industry. So being attentive and being on time are two of those things which are really quite important when you leave this place. So my policy is that class will start promptly at 10 minutes after the hour. Please be respectful if you're entering class late, because it's going to be distracting for others. So please find a seat as quickly as you possibly can. If you're coming in late, and causing a ruckus, don't be surprised if I call you out. So that's directly related to why I'm currently here in Vietnam. This is actually the title slide from my pitch deck I'm going to be using later today in the Aquaculture Innovation Challenge. What I'm going to be doing is pitching our idea for a wind-powered aeration system, which can help improve water quality for rural fish farmers. So I'll tell you a little bit more about this technology and other research topics we have going on in my research group as we go on through the semester. So I'd like to take a quick minute and just introduce you to your TAs for this year. So you have your tutorial TAs, Talha and Onaiza.
Hi everybody, my name is Talha. I'm a second year PhD student from Turkey. I will be your tutorial TA this semester. I've been working on MEMS sensors and smartphone optics in my research studies, and I'm pretty excited about this new year because it's a fresh start, and I hope we can help you build some knowledge about control systems. So come to tutorial sessions, meet me there, and don't hesitate to contact us. See you around.
Hi, I'm Onaiza. I'm a third-year PhD student in mechanical engineering. I actually did my undergrad here at the University of Toronto as well. I'm from the microrobotics laboratory, and in our lab, we actually use various different control techniques as well as design some of our own in terms of formation control. For this course, I'll be one of your tutorial TAs, and I'm really excited to TA this course because I know for many of you, it will be your first experience with control systems and will allow you to really solve some practical problems.
And your lab TAs, Amro and Francis.
Hi everyone, my name is Amro Ibrahim. I'm a PhD candidate in the Mechatronics Design Lab. I'm excited to be with you in this course as a lab TA. Together, we will learn how to create dynamic systems models and how to build controllers on MATLAB Simulink. We will also learn how to tune these controllers for different applications to meet specific performance requirements. I wish you all a great learning experience in this course, and I wish you success. Thanks.
Hi, my name is Francis. I'm a master's student in the Water and Energy Research Lab with a background in power electronics, control systems, and energy. I'm going to be your lab TA for MIE404 this semester. I look forward to being your lab TA since the labs are designed to be very hands-on and engaging, and I hope that you would be able to walk out of the labs in the course and with the knowledge that you've learned and used and be able to apply them in the future. Thanks.
So what are we going to be doing in the class? Really, it can be broken into three main parts. So we're going to be looking at modeling a system. So we're going to be taking sets of hardware, and then we're going to be using our knowledge of physics to be able to develop sets of dynamic models, which for everything that we're doing, these are going to be ordinary differential equations, or ODEs. We're then going to take those models in the next step and look and understand, based on properties of those equations, those models, how a system will respond if you apply different forces or other types of inputs. So we're going to look at the system response. And then finally, we're going to look at how you can take sensors, which are measuring what a system does, how it responds, and then modify how the system behaves so you get a desired response. So we're going to go from response to desired response. And we're going to do this for a range of different systems. So there's lots of examples of control systems out there. The first examples were actually fully mechanical control systems, such as the flyball governor. These were developed by Watt in the 1700s, and it was used to actually control the speed of a steam engine. So it's meant to keep the steam engine rotating at a very constant speed. You can see this control system in operation in the video on the left. So as the steam engine here is turning, it's connected via a belt to this mechanism you can see here with the balls rolling around. So how this works to regulate the speed of the engine, so it's trying to hold the speed very constant, is it's actually coupled to a valve. So you can see the valve in this image on the right. So if for some reason, say that the steam engine may speed up, maybe it's driving a locomotive and the locomotive starts going down a hill, but it wants to maintain a constant speed, what actually will happen is if the engine starts to speed up for some reason, is it's going to actually rotate this shaft here. And if it starts to speed up, these balls are going to move further out because it starts to go faster. So as it starts to go faster and those balls move out, it actually then pulls down here. And then because of the pivot, we'll pull up here. And in turn, we'll start to close this butterfly valve. So if it starts to speed up, it's going to close the valve, and then it would provide less steam to help the engine slow back down. Similarly, if it started to slow down for some reason, the balls would start to fall and it would open up the valve to be able to provide more speed. So this is a purely mechanical system that takes the output from the engine speed and then determines how much steam goes into the engine. And it works to regulate the speed. So there's lots of examples of control systems out there from across many different domains. In the field of robotics, controls is, and almost every single robotic system you're looking at, where you're trying to have any type of precise control, you have some measurement of what's going on with your system, which is then being fed back to be able to determine how to drive different motors or different inputs to the system. Similarly, there's lots of examples from across the field of energy. If you had an example like this solar concentrator, you could look at, you're trying to regulate and determine the exact position for pointing of this solar concentrator. So you could be measuring the angle and then feeding it back to, again, control a motor to be able to make sure that your solar concentrator is pointing where you want it to be pointing. Okay, so with that in mind of what we actually want to do and what we're going to be talking about in this class, we can look at what are the actual objectives. What do I want you to be able to do by the time we reach Christmas? So what I want you to be able to do is to be able to look at different systems, be able to use our knowledge of physics to be able to develop different models for those systems, be able to take those models, look at different properties of them to be able to understand what the system stability is and how it's going to respond to different inputs. And then we're going to be able to use all these really cool tools to be able to analyze the aspects of the system, root locus, Bode diagrams, which you might be familiar with from third year, Nyquist diagrams as well, to be able to analyze these systems and then use them to be able to design control laws. So different logic in terms of how you take an output of a system and be able to get your system to behave how you want it to. And then finally, I want you to be able to apply control laws to be able to regulate different hardware systems. So how we're going to do that is through our different course components, our labs, our lectures, our tutorials, our class projects, our tests, and what we're going to be doing in our readings from the textbook. So going through the different components in the course, we'll start with the labs. Labs are not going to actually start for a few weeks. We're going to start the labs the week of September 25th. And we're going to do a slight reorganization on the labs this year. We're going to actually only have 4 labs this year. So don't all thank me all at once, but only 4 labs this year. And we're actually going to be using the new sets of lab equipment. So last year we configured some new equipment, which I think is really cool. We worked really hard to be able to put these together. So we're going to be using this new equipment we put together to look at using control systems to help regulate operation of a power grid, as well as using control systems to be able to regulate position of an airfoil in a wind tunnel, which I think is going to be, is really going to be great. So you're going to get a chance to be able to work through some of that new lab equipment. So you all have your lab sections defined, but there's too many of you in each section to be able to have everyone go all at once. So we're going to actually be breaking into each section is going to be breaking into half into 2, and I'm going to ask you to go online to specify which of those weeks you want to go. If you want to go in the first set of weeks, which are going to be doing individual labs, or the second set. So you can go online and you can fill in the online form to be able to do that. Note that attendance is required for those labs. We will be taking attendance. The TAs will be taking attendance. And after the conclusion of the lab, you'll have a little bit of time to finish up the report. And we want those to be handed in the week following the lab on Friday. So for the lectures, we're going to have 2 lectures a week, one 1-hour lecture and one 2-hour lecture, both in MC 252. Note that for that 2-hour lecture, I know it's going to be really tough to pay attention for 2 hours. I know it's tough for me. So we'll take a little break in the middle of that 2-hour lecture. So for our lectures, what we're actually going to be doing is we're going to be following a format very similar to what you're seeing in this video today. So I'm going to be providing a set of base lecture notes, and they'll be posted before each lecture, at least the day before each lecture. And there'll be some blank aspects that we're going to be filling in during the lecture. And I'll be posting the notes with some annotations after the lecture, but there may be a few additional things I bring up in the lecture that might not be in the posted version online. So I really encourage you to print out those slides, bring them in with you, and fill them in with us when we're going through lecture. So there's a full schedule. You can take a look at what we're going to be talking about. But really, we've got those 3 main parts I was talking about before, the modeling, dynamics and stability, and then looking at designing control laws. And then finally, we're going to look at, just at the conclusion of the class, other ways to represent systems for controls using state space representation. So we will have tutorials in this class, once a week, a 2-hour tutorial. So there's going to be 2 sections. And in those tutorials, the TAs will go through and review sample problems and review areas where I think there's a need for extra instruction. In addition, in those tutorials, we'll have some short quizzes at 4 different points throughout the semester, just to help you keep up to date. They're not worth a whole lot in terms of the overall mark, but they're meant mostly, just to keep you on track and keep you up to date, and may help you to realize if you're falling a little bit behind on some of the items. So throughout the course, we're going to be using this book here, Feedback Control Dynamic Systems. We're going to be using it in the context of some of the tutorials. Some of the sample problems will come from this textbook, and you'll be able to use it to help further explain some of the concepts we're going to talk about in the lecture. It's currently available in the bookstores, but the other thing to think about when you're thinking about this textbook is that the midterm and the final exam are both going to be open notes and textbook. And the only textbook I'm going to accept is this Feedback Control Dynamic Systems. If you want to use an international edition or a previous edition, that's fine as well. But just keep in mind when we're going through the semester, some of the examples will be slightly different if you're using those versions. Okay. As I just mentioned, the tests are going to be open lecture notes and textbook, so make sure you get that textbook as a reference. And we've got a date set for the midterm. We're looking at October 27th, and it's during that lecture hour, so you shouldn't have any conflicts. But if there are conflicts, please let me know about it early. We can try to see what we can do to adapt. If there's a huge portion of the class that has another midterm, directly following this slot, just let me know, please, as early as possible. So last but not least, we're also going to have a project in this course. These are going to be conducted in small teams of 2 to 3 students. And we're going to involve doing some modeling, analysis, and then doing a control system design for an individual system. So we're actually in the process of revamping the project for this year. And we're going to hand out a bit more details about those projects in the midpoint of the semester. So all those pieces come together to be able to determine what's going to be your final mark in the class. So we have our labs at 10%, quizzes at 5%, midterm at 20%, a project towards the end of the semester at 15%, and then that final exam at 50%. So I'll take some time at the beginning of the lecture on Monday in case you guys have any questions about the structure of the class and the deliverables. Okay, so we've gone through the boilerplate for the class. So now let's take a look and really understand what we're going to be talking about when we talk about control systems and what we're going to be studying in this course. So just to overview some terminology we're going to use in this class, we're going to use the term system a lot, which is really a combination of components that act together to perform a function. And we're going to represent these systems a lot graphically. So basically these systems will typically have some sort of input, which we're going to call U of t. And then it's going to map to some output. So let's think of an example of a system that we were just looking at before. Let's think about the steam engine. So we can think about the steam engine as a system with the input being the steam going to that system, and then output being the speed of the engine. So we can also think about a control system, which is really an arrangement of different components that are connected together to command or regulate a system. So in a control system, what we have is we have some reference. You can think of that speed that we want that steam engine to go at. We're going to call that R. And we have an output from that. In this case, it's going to be U. And we're going to be taking measurements to be able to determine what that output is. So in the case of that purely mechanical flyball governator system, the measurements that we were actually taking, we were actually physically measuring the speed using those balls on the flyball governator and centrifugal force to be able to then determine the position of that valve, which regulates the steam going into the system. So something we're going to be using throughout this course is block diagrams. and I think most of you have seen these before in some of the context of some of your other courses. But what they are is they're a graphical way to represent a system. They can also be used to represent different mathematical expressions, and that's what we're going to be using them to do in some of our examples as we go through the rest of this lecture today. So there are a number of different blocks you might have in this block diagram, but in the examples we're going to be going through, there's going to be two main different types of blocks. We're going to have a gain, where you basically are multiplying some input u by some value. So writing this out here, if I'm writing this out as an equation of what happens here, y is equal to k times u. So you just multiply this input by the value in the block. You may also see blocks which are addition and subtraction. So if I'm going to have that here, I'm going to say I'm going to have x, y, and z. What this is going to actually be mathematically, it's the same thing as saying z equals x plus y. And you may see these addition subtraction blocks also drawn like this as a circle, with lines coming in and some plus signs next to it. So these are different ways to write out some different mathematical expressions as well. And don't worry if this is a little bit confusing. The first tutorial that you're going to have is going to go through and review block diagrams in some more detail, which will prepare you for your first lab where you'll be using block diagrams in lots of detail. So with that block diagram example and our definition of a system and control system in place, we're going to look at an example of a parabolic dish solar collector and what a block diagram may look like for this particular control system. So here's an expression of that sun tracking heliostat as a block diagram. We can look at this and we can see which part of this actually represents our system and or you may also hear the term plant used. We'll use it. And then we have our output, which is then being measured. So we've got measurements, which are then being used to determine the actual torque which is being applied. So that is actually means that this whole entire part is a set of components that are used together to be able to control or regulate a system. So this is our control system based on the definition. Which is taking that reference to be able to regulate the system. So now that we have an idea of what a system is, which is a collection of components which serve a function, and a control system is, which is a collection of components which are meant to regulate a system, we can look at two main classes of control. So we're going to start with open loop control. So in open loop control, what we have is we have our output from our system, y, is not fed back to be able to determine what our input is, u. So we can say the input to our system is not a function of our output. So there's no measurement being done to be able to determine what that input is. So an example of something like that is a light switch. Our input in that case is the position of the switch. Output our lights on or off. But there's no measurement going back of what the lights are actually doing to be able to regulate what's going on. So to contrast with open loop control, the other class is closed loop control, where the input to the system is a function of the output. We're going to have lots of examples of this as we go through the class. But to start, I'm going to think about and pose a simple thought experiment about a biology-based example. So say I was going to reach out and touch an object. I'm going to tell if I'm going to be close to that object or not by using my eyes. I'm going to be able to have my reference of the object I want to touch and my position of my finger that I'm looking and measuring and feeding back. Then what I'm seeing is them being processed by my brain. And then I move my muscles to move my finger to touch the object. So we have here, we have our eyes. These are our sensors to be able to tell what we're doing. Our brain is our controller. Muscles are actuators, and finger, this is our system, our plant. So in closed loop control, what you're doing is you're taking measurements, feeding it back, and using it to determine your input as a function of those measurements of your output. So let's think of another biology-based example of a control system. In Vietnam, there's crazy traffic everywhere. As a driver of a motorcycle, you need to be able to look and observe your environment and then provide feedback to determine where you're going to go. They even need to be able to think about crazy pedestrians that might go out and cross the road, like this. and use that as feedback to adjust their steering and avoid any hazards, like Professor Bilton. So we're going to be seeing a lot of diagrams that are going to look something like this as we go through the semester. So just to clarify what's meant by some of these boxes that you're going to see in this diagram. So if we're looking at this control elements here, what's really meant by that control elements is the control logic that we're going to be talking about. Actuators, and electronics. So those control elements, they use that feedback signal from the feedback elements. And really what I'm meaning here is sensors, and the last part I want to kind of clarify here is what's actually meant by disturbance. And really a disturbance is anything that when you're going through and you're developing your model of your system or your plant, disturbance is really anything which is unmodeled. So it could be, if you're thinking about that solar concentrator, it could be wind hitting that solar concentrator. It's not something you have modeled, and it's going to cause some disturbance to your system. So there's two main types of controllers that we're going to be talking about in the scope of this class. We're going to be talking about regulators, which is something which is trying to control the output as close as possible to a constant desired value. So when you're thinking about regulators, that flyball governator is an example. It was able to regulate the speed of that steam engine. You can think of lots of other examples. Thermostats, regulating a constant temperature, cruise control, regulating a constant speed for a vehicle. But you could also have a controller which is trying to track something which might be varying over time and trying to track it as closely as it possibly can. So you can think of things that are changing over time. So that might be different robotics types of applications, self-driving cars, lots of other examples. So we've talked a little bit about feedback control or closed-loop control. So why do you think you might want to use feedback? So thinking about that example of that solar concentrator, let's think about like if it's windy, right? If it's windy, you might not be able to track the sun very well. But if you have feedback control, you can actually reduce the sensitivity of those type of disturbances or unmodeled dynamics. We can also improve the system autonomy, make it so a system can operate without continuous human intervention. We can make it so our system has better agreement between a reference and our output. And we'll talk a little bit more about what this means a bit later in the class, but we can actually improve the stability of our system. And we'll show this later in the class as well. We can actually make our system so it's going to be able to respond quicker. Okay. So we're going to take a quick look at feedback control and understand how it actually really helps to be able to get your output to be able to match your input. We're going to look at an example of controlling speed of a vehicle, or cruise control. So we're going to say here, we're going to choose some value for this controller that's going to be able to allow us to be able to get that actual speed to match the desired speed for our cruise control. Okay, so before we look at what the feedback case looks like, we're going to start with an open loop case. So let's say we want to be able to match that output speed y equal to our input r. So y equal to our reference r. So in order to take a look at this, we're going to start by writing out the block diagram algebra. So we're going to actually look here and say what y is equal to, it's going to equal 10 times the sum of u minus 0.5 w. We can expand this out because u is equal to k times r. So since w can be positive or negative, and we can only choose one value, and the goal here, what we're doing is we're trying to determine what that k is, which is a constant value, and w can be positive or negative, we're going to make the assumption here that w is 0. And we want to make y equals r. So therefore we have our k equals 1 over 10. So we've got y equals r minus 5w. So we can actually see what our error would be, right? Because if our error here is going to be r minus y. So this is, we want r to equal y, so our error is how far r and y are apart. It's going to equal 5w. So if we are trying to design a cruise control system without feedback control, we're going to have this error in this case, which is 5 times the road grade. So what happens now if we close a loop? What happens if we now put this extra line here, this one, to be able to compare our reference to our output? So let's start just doing some little quick amount of algebra. So we're going to write out what y equals again. So y is going to be 10 times, similarly to before, it's going to be u minus 0.5 w. So this is the same as what we had before. But now, if we're taking a look at u is equal to k r minus y. So a little bit different. So let's combine those two equations that we had from before. We can substitute u into the equation for y. And expand things out. And let's just rearrange things here. And we'll just do a little bit of cleaning things up. So we've got an expression here for output y, right? So let's say we choose a value for k the same as what we had before. If we do that, we would have the following. So there'd be a slight difference between y and r, very, very small, but the sensitivity to the noise or the road grade is much decreased. So we're able to really bring down that sensitivity to the unmodeled noise. Also, if you increase k more, the error will go down, right? But there's other complexities when you increase k. And we'll talk a little bit about that. It's several weeks off. But you might have problems with stability. We'll talk about that as we go forward. Okay. So feedback can have a huge impact to be able to make sure that you're able to get your output to match your input when you have this type of noise. So just to wrap up this lecture, what is it really that we're going to be doing in controls? And what are the objectives of controls engineers? Really, what you want to do as a control engineer is you want to be able to select and put together control system components to be able to achieve a desired system performance. And that's really looking at being able to choose everything from sensors, actuators, and control logic, etc., to make it happen. The first step to be able to get there is to really understand what's going on with the system and how the control logic influences the system performance. So that all starts with development of system models and then analyzing the properties. And this is really what we're going to be doing next. Okay. Okay, so just quickly review what we talked about today. And what I want you to really remember from this section of the class is what is control? Really being able to take information about our system, make our system do what we want it to do. What are the elements of that control system? And why you want closed loop control. And in the end, that's to be able to limit the impact of uncertainty, increase the robustness, and improve stability. We're going to be starting talking about models in the next lecture. I'm looking forward to meeting you and talking to you about models on